Awesome. Welcome, friends. This is another session with Deep Learning Adventures, a fun and engaging meetup where we talk about deep learning and data science in general. And we look at coding exercises, we look at different resources online. We try to expand a little bit our knowledge with other resources that we put on our own. And really the goal is to learn from each other. So if this is your first time here, welcome. If you've been before, again, you're in for a treat, and good to see some old friends, and looking forward to making some new friends as well. If you don't mind being mute, unless you have a question, that'd be great. And today I'm joined by my great friends and co-hosts and co-organizers, David, Robert, and Dimitri, and we have a fan-packed evening for you, so stay tight. With that said, let me post some information on our Slack, on our chat here about our Slack information and some other resources where you can find us. So this session is recorded. It will be posted tomorrow on our Kaggle Courses YouTube playlist. And I also posted a link on our Slack channel in case you want to join us and ask more questions and take a deeper dive in your code or issues, or just get to know each other better. Cool. With that said, let me enable share screen. And I think, David, you're first, if you don't mind kicking off this intermediate machine learning adventure we're about to embark on.
Can you see my desktop?
Yes, introduction.
All right, so we're going to be talking about Kaggle's mini course called Intermediate Machine Learning. If you didn't join us before, when we went through the introduction to machine learning, I think you'd find that very quick to go through and straightforward. And you can find also our coverage of it on the our YouTube channel, which I think George has already posted. But if you're familiar any at all with machine learning, a little bit of Python, I think you'll be able to follow along. So in this intermediate course, we're going to talk about the type of data that we find in real-world data sets and some of the messiness that comes along with that, such as missing values and different types of data and how we can handle them. If you recall, machine learning models like to work with numbers. So we're going to talk about the fact that a lot of data is not in the format of numbers and how we deal with that. And then we're going to talk about some pipelines, which when you're manipulating data, it's nice to have a repeatable process that you can use on different parts of your data. So go through pipelines. And then a neat technique called model validation, where we use cross-validation to validate that our model is not just good on the little bit of data that we trained it on, it may actually be good for unseen data. Then we're going to cover one of the neatest models for machine learning called Xgboost, and find out a little bit of theory behind that. Last time, if you recall, we talked about decision trees and random forest, and this is now a step beyond that to a boosted model. And then the last thing we'll cover is a very important thing that you see a lot when models have fabulous results. It probably means you've got some kind of data leakage in your system, and we'll address that. So that's about it for the introduction. They have an exercise here, which we'll go through that goes with this. And it's basically an introduction to one of the data sets that we're going to work with. And I just want to say, if anybody has any questions at any point, you can either post them in the chat or go ahead and unmute yourself and ask me. Don't feel shy. So the data set we're going to look at is a pricing competition for housing data. So this is the sales price of houses in different neighborhoods that are different types of houses with different characteristics. And in here, we're going to pull it in. There's the training data and test data, and they happen to be in CSV format. This is not really the pandas course. That'll be later on. We have a micro course on pandas that I think Kathleen's going to go through. But just in essence, here we're just reading in those into some data frames is what we get out of here. And the target that we're going to look at, as I mentioned, was sales price. And then there's various features that we can select out of this data set to use, such as the size of the lot, the year the house was built, the square footage on the different floors, how many bathrooms and bedrooms there are, and such. We're going to call that our X values. And then the Y values are, of course, our target, which is the sales price. I think last time we touched on how to use sklearn's train test split to create our training and our validation data. Here we're setting aside 80% of the data in X, which is our training data. We're going to use 80% for training and 20% for validation. We're going to take a look at the data that we've got out of the data set. In this case, it's all numerical, which makes it nice and easy to work with. And then we're going to create a bunch of, actually 5 different random forest models with a couple different parameters to change the way the models are created and work. And then we're going to run those models, run the fit on them, do predictions, and then look at the mean absolute error, which this is a regression problem where we're trying to predict a number. It's not a classification number where we're trying to predict, a type or a class for the result. So we're looking at a number. So we're evaluating mean absolute error to see how far we are off from the true value. So we're going to do that for all our models and print out the scores. And the question in this exercise is which one has the best score. And since we're looking at an error value, the smaller the better. So that's why number 3 here is the smallest value, might be the answer to the question. So I just want to make you familiar with that data. You can then go and once you've done your training, you can pick that best model. I think this is probably the best model that they used that we write in here, and we're gonna actually fit it, make predictions based on that from our test data. And if you want to, you can submit it to a competition they have set up for Kaggle learners, which I do advise you to do so that you can see how that's done, how to join the competition and submit a submission. And then after you do that, maybe go back and play with it.
We have a request in the chat. If you would you be able to enlarge your screen?
Absolutely, yeah.
And we have also a question from Asveta. Hope I'm saying that correct. You can correct me if you like. Why mean absolute error as our metric here?
It's a good question. So in a regression problem, you're trying to predict a number, in this case a sales price, right? So that's the essence of regression, is predicting a single value. One way to look at how you're doing across all of the training set, which if we go back to our data frame, every row in our data frame has, maybe we can see it, but well, they don't show the whole thing, but has features that represent a single house. And then we also have another set of data for prices. So then, in the original data set, there was a column here for sales price. So for each house, we're trying to predict that. Well, in general, I want to know how close I'm getting to the real price within my whole data set that I'm studying. And I want to get that value to be as small as possible. So whether I'm negative, below the price or above the price, in this case doesn't matter. In some types of problems and data sets, we may be more concerned about being below or above the actual number we're trying to predict. But here, I just want to know how far away I am from the actual number, so the absolute value. So that's why we've chose the mean absolute error as a way to evaluate our model as the metric we're using. Does that make sense? Hope that answers the question. If not, follow up with me.
Yeah, mostly we are using the mean square error instead of mean absolute error. So I was looking some reason. I know in the L1, L2. So the absolute is when you focus. I mean, there are some specific needs when I know people are using the absolute error measurement.
Yeah.
So I'm looking if you have some reason, why you choose instead of the mean square error.
So I would use it for the metrics. They're using it also. I don't know if you see right here where they're defining their random forest. They're actually using it for their loss function too. I personally would probably have used mean square error for the loss that I want to minimize. So I would have used MSE for the loss, and then for my metric I would have used MA probably.
All right, thank you.
Yeah, it's just a choice they made for ease of showing it here. All right, so I'll go to the next.
But before you go there, David,
Go ahead.
Dimitri also posted some intuition YMA in terms of the units, so it's easier to interpret how far you're off from your baseline. Right? It's easier to interpret that you're a few $1,000s off versus a few $1,000s square off.
Yeah.
Question for you, David. What was the difference between the different models? Was it just number of trees and some other criteria?
So a lot of different things. You can see in one case they're changing the number of trees from 50 to 100, 200. They use, I think actually they are, okay, so here when they did this test, I think if I recall right, in random forest, the default criterion is MSE, and they changed it to MAE for this one model. And then in a couple of cases here, they affect how far down they go, and there's a lot of, it's how the behavior of the model is when it trains, if that helps. They've changed some things that will differentiate the way the model trains.
That sample split equal 20, is that the requirement that you need at least 20 samples before you branch to a new level?
I have to go look at the different random forests.
Most of these are trade-offs. Most parameters to most machine learning models, honestly, are somewhat of a bias variance trade-off, right? So here, min sample split for random forest requires that if you don't have at least 20 samples at a particular leaf in the tree, you're not going to split it again.
Right.
So think about the implication of that. If min sample split is too large, you could end up with a very biased tree because it's just not deep enough. If min sample split is very small, you could end up with a very overfit tree. Max depth functions kind of the same way, where it's really a trade-off between underfitting and overfitting.
Yeah, how far you can go, how many splits and everything.
Cool.
Okay. Then the next thing we're going to talk about is the next chapter is what do we do if we have missing values in our data set? So a lot of times, not every row and every column will be filled in. We may be missing data, and that may make sense. We saw earlier in our data set, we had first story square feet and second story square feet. Well, what if we just have a one level house? Then it doesn't make sense for that value to be in there. There's also cases where they mentioned like surveys and things like that, where people have the option of not responding. There's many other reasons why you may have data that is not complete. So how do we deal with that? Our most of our models expect there to be values in all the columns for them to function correctly. An example of 3 approaches they give. The first one is that suppose you're missing a column and you have not a number in there or a null. The first choice you can make is to just drop that column because we've got missing values. Well, that's a very brute force approach, and it may work when you have no real meaning to prediction for that column. So if no one cares about the number of bedrooms in a house and it makes no difference on the price, then you would be safe to drop this column. I suspect that's not the case, but we'll test that. Another option is known as imputation, and this is a whole field of research here, but we're going to look at some of the most straightforward imputation approach, and that in this case for numeric values like this is to take the average of all the rest of the column, all the rest of the rows in that column, and substitute in for our missing values. So in this case, we've got 1, 2, and 3, the average or the mean for that column then would be 2, and so we're going to put 2 in. This can work well in some cases depending on the data set, but a lot of times this can be a bad choice as well. Another thing to do is basically to make a record of when you're missing this, and you put in this case, you did some type of imputation, but you're also going to create a new column to show that this was a special row in which you did that imputation. So we're going to create a bed was missing and mark it as true for this one value. I've also seen people put special values instead of taking a mean. Maybe that makes sense to put a really outlier, unusual value that the model can interpret. That a lot of times doesn't work that well, but sometimes it might for special cases. And there's a few other approaches for how to handle missing values. For instance, there was a lot size, I believe, was one of the features that we have in our housing data set. And if, say, one house didn't have the proper it had no lot size in it, we could, if we had some type of geographical data, or maybe even at the neighborhood level, we could do an average of all the houses in that neighborhood, their lot size, and assume that this one is similar. So that may work in a case where you've got neighborhoods that are all built at the same, houses are all built in by the same builder in the same neighborhood at the same time. That would be a good choice. It may not be where you're, out in the countryside where lot sizes vary a lot. But that's just another, there's many different ways you can handle these values. So we're going to look at the Melbourne housing data set. It's a different data set that has some more of these problems. And we're going to look and see what columns have missing values. And the way we're doing that is we're looking at the data set for that each column, which then we're going to do the isNull.any. So we're looking to see if there's any null values at all. You can also use there's another command here which is synonymous, which is the isNA. So if you like to type less like me, you might use isNA instead of isNull. And then we're going to go into the train and the validation set and drop the ones that came out to be true and entered and got into our system. So we're going to drop those columns that have missing values, and then we're going to run our prior method of fitting and prediction and doing our scoring. So doing approach 1, we're within a price range of 183,000. So we're pretty far off, but this is our baseline. But let's take approach 2, which, if you recall, was imputation by putting the mean value in place of the null values. So again, we're going to do this anywhere we've got these values. We're going to use the simple imputer, which is a library from sklearn. It finds all those missing values, columns and rows where they're missing, and it's going to put it in there. We will do something very important here. This is like a transformer of data. And one thing we're going to do is on the training data, we will do a fit where it will look at all the values of the training value for that column and calculate the mean. And then the transform will go and fill in the nulls that are present there. However, on the test data or the validation data, we're not going to fit the validation data because that represents a form of data leakage, which we'll cover later in this course. Instead of that, we're going to do just the transform. So we're going to, in this case, it doesn't make a lot of difference, but it can, because we're using the mean of the values in the training data to actually calculate the missing values for the validation, the unseen data. So this is how you would do that. And then we're going to imputation. This particular thing happens to remove the columns for the places where it did the imputation, so you have to put the column names back. It's kind of a weird quirk, and I wish they would kind of fix that. But then we're going to do our scoring, our fitting, our training again, and we actually get 178. If you recall, before we were about 183,000 away, so we've improved our error some here with approach number 2.
Question
putting in
for
the mean.
it.
Go ahead.
Yeah, question.
Yes.
Yeah. So how do you treat for the categorical variable when you come to imputation?
So we'll go through it in a second.
Okay.
The next chapter is on categorical variables, and if I don't answer it there, please remind me. Okay. So the next approach was the third one, which was we're going to do the imputation with the mean, but we're also going to create a new column to mark the rows where we actually did imputation. So again, we're gonna put in a new column, was missing, and we're gonna mark it as true or false depending on the value. And again, we're doing the fit and transform on the training and just the transforming of the validation set. Have to put the column names back and we score it. And it gets 178, which actually, if you go back to the prior, 178, 166, and here it's 178.97. So we're slightly worse actually. So this, in this case, did not improve our results, which is an interesting feature. I actually think it has a little bit to do with the fact that we used well, we'll see it in the exercise, but I think we used a pretty small random forest number of trees. So I'm not sure, but I would like to test that. So their hypothesis is that dropping columns removes a lot of useful information, and so it makes sense that imputation will perform better, but they don't really explain why approach 3 and approach 2 didn't differ very much. So I hope that helps. They wanted to also show you how you can look and see how many values are missing from each one. Instead of doing the .any to detect if any are missing in that column, you can sum and print it out. It'll print out the missing ones for you. We can see that car, building area, year built. Car is a good one. It might be missing because I think this is a measure of the number of cars in the garage. And if you don't have a garage, maybe you don't have a car, you know. So different things. Some of these might be a challenge. You might be able to look at the neighborhood averages or the mean to get some good values for building area and year built. So if there's not any questions, let's go to the exercise and see what they do. All right, so we're going to go back to our.
So there is a question in the chat.
Yes, please.
So from Madison, can you fill in values for columns based on values of other columns? For example, if a house is 50% larger than average square foot, can you set number of beds as 50% more than average number of bedrooms? So
absolutely,
asking, yes. Like, can you do more complicated imputation?
Absolutely. So there's really, as I said, it's a whole field of study almost, all the different types of imputation you can do. And it's basically a very advanced form. It can be a very advanced form of feature engineering. It becomes almost beyond what would be termed imputation. Imputation a lot of times is just dealing with a single column. Hope that answers your question. There's a lot of different strategies. The housing data set is a great.
In that case, you could even do just like a custom pre-processing step to define another column.
Right. Right.
Is that done within the sklearn environment, or you have to do it on your own, David?
Using other columns?
Yeah.
It's usually, so I think what they're talking about is you would mainly do it with more something like a pandas approach.
Okay.
Yeah, I don't think there is a package in sklearn itself in the imputer.
Yeah.
So basically, if the column is you think it's informative, and so maybe you don't have much data, but you think that feature is really important, then you would treat it as a separate target and then try to predict it, and then add to the predictors.
Yeah, that's another approach. And then you can get more complex and put target weights on it and that kind of thing. But so we're going to look in our exercise, we're going to look at the housing data again that we looked at before for the Kaggle competition. In this case, we're going to not just include a few columns, but a lot more columns. We're going to look at all of the numerical columns. So here we're excluding objects, which are going to be your strings or categorical columns, and we're only going to look at numerical columns. So we're going to do very similar to before. Now you can see we have a lot more columns than prior. And you might notice a few, there's like an NA here and lot frontage, or maybe some other ones, I'm not sure. But so we got some missing values that we're going to have to deal with. First of all, let's get a sum of what columns have missing values and print those out. And here you can see we've got 36 columns in total, 1168 rows in our training. This is our training data, and we have 3 columns where we're missing data. Quite a lot on that lot frontage that we already saw, but masonry veneer area. Some houses may not have a mason veneer, so they may not have a value. Garage year built. You can imagine if a house doesn't have a garage, this is going to be empty. So some good examples of why you might be missing values. They ask us to, analyze that result that we just got out. And now we're going to talk about the best approach for dealing with this. Obviously, they want us to use imputation. We're going to set up our score data set again, which is just a helper function to create our random forest. Here we're using 100, which is better. We're going to do our fit and prediction of the valid, and look at mean absolute error again for our metric. So we're going to use the similar approach that we did before. We're going to drop those columns that are missing values. Same thing we did before. And we're going to run that with our score data. And now we're missing the price by only 17,837. So that's with MAE with missing, removal of columns that had missing values. What if we do take the mean with a simple imputer? Simple imputation here. We're going to do that. We're going to run that, and we're going to get us worse result. So now we're a little higher. We were 17 something. Now we're at 18. So obviously taking the mean didn't work. And why might that be? I would guess that putting in the mean for some of these doesn't make much sense. Maybe the houses that don't have a lot of lot frontage, I don't know if those would be, I have no idea what kind of those there could be quite a few houses that are not on, pipe stems or something, so don't have any lot frontage maybe, and it doesn't make sense to list that. I'm not sure how that affects the price, but apparently it does. And anyway, it wasn't a good idea just to do the mean. It was better just to drop those, not consider them. But what about doing, let's see, we're going to now think about another solution. Are we? Nope. That's it, right? Yeah, so we didn't do another one, I think, right? Or did we? Did we do 1, 2, 3? Sorry. Yeah, so that was it, right?
Yeah, I don't see another one.
So we didn't try the other step where we added a new column to note whether we had done imputation on it or not. So here's some values. There's a lot of other forms of imputation, and I invite you to kind of explore some of the ones that are available in sklearn, or hand code yourself some and see if you can improve the scoring for this competition. So any questions about this? This is pretty much just what we saw on the other page. So let's go on and talk about categorical variables, because that's kind of interesting. When we don't have numbers, what are we going to do? So categorical variables have a limited number of values. They could be words, such as this. I will tell you that categorical variables can also be numbers, and maybe I'll give you some examples in a little bit once we go through this. So just because you have numbers doesn't mean that you have numerical data, just continuous data. You may have a category and you don't know it. So there's 3 approaches to categorical variables in our data. We could just drop them, sort of what we saw before sometimes. This would only work well if the categories themselves have no value that has any correlation to our prediction we're trying to make. Here's where I have a real disagreement with this training. They talk about label encoding. I guess in a general way, that's fine to say label encoding. I'll show how they implement it. That's where I maybe have the issue with what they've done, but we'll go through that in a second. So label encoding means that we've got categories and we're going to assign each unique value a number, an integer, right? For this case, like every day is going to be 3, never occurs in 2 rows, and they're both going to be the same number. So they're both going to get 0. But they're also introducing a ranking here. So we're saying that the reason we're giving never 0, because it's apparently less than rarely, it's less than most days, and certainly less than every day. So we're inducing an ordering or a kind of a ranking of the category labels as well. This ordering is called an ordinal variable, and that's one new approach that we're going to take. We're not losing our category variables, not dropping them, but we're encoding them with ordered numbered labels that then our our model can use. There's one additional way to do it, which is there's many additional. Sorry, I'll talk about others, but the next one they introduced is a very popular one. It's called Hot Encoding. You may have heard it as dummy encoding is another thing. Pandas can do this for you. It's dummies as it's called, but Hot Encoding is the most popular terminology for it. And in this case, we're going to introduce, in essence, a vector that has shows us whether, not a vector, but sorry, we're introducing new columns to replace the original column that are basically named after the values that the color or this column can take, right? So we're introducing 3 new columns because that's our discrete number of variables we have here, or categories we have. And in each one, we're going to note whether true or false the value is in our color over here, right? So typically when you do this, we would introduce these 3 new columns and they're all true or false, depending on if they have the value over here in the category. And then we would drop the category or the column on the left. So color we would now remove because it has no more meaning to us, and it's categories anyway, not numbers. But now we have Hot Encoding. This is a very good way to do categorical encoding for categories that have a small number of possible values. So it's called the cardinality is basically what it means. But it's if you notice, every different value that's possible over here is going to introduce a new column in your data and a whole new set of numbers. This is possible that you introduce so many new features or columns that your data set becomes so large that your model runs really, really slowly, and it becomes impractical to introduce so many new columns and features in your data. When we don't have, the other thing I wanted to note also is there's no ranking here or ordering to the values, whereas before when we did label encoding, these had very specific rankings within the column. Here it's just basically a true or false. Is it there? Is it present or not? So red is no more important than yellow, is no important than green based on these numbers. Our model, when it does its training, may find that yellow is more important than green or whatever, but we're not saying that when we move over to this type of encoding. Those are called nominal values. So the example here, we're going to go back to the Melbourne data set, and we have a couple of categorical variables or features here. So method, region name, and type are all going to be strings. The other ones are interesting. Clearly, most of them are straightforward numbers and have meaning as numeric. Postcode is an interesting one. You know, is there something to say that a larger postcode is better than a smaller one, or vice versa, or somehow it has an effect? This is one that you might consider thinking about a different way to handle. Is this actually a categorical variable that's a number? I would suggest it might be, but they don't talk about that here. So let's just talk about the very straightforward strings. So here we're going to look at everything that's a string, so an object type in our data set. We're going to change those. We're going to label those as category variables. We see type, method, region name, the 3 strings we have. And we're going to do approach number 1. We're going to drop all 3 of those columns and see what kind of result we get. So we do that, we run it, we get 175,000, right? Approach number 2, where we do the label encoding. Here's where I think we have the issue with label encoder. And I'll go through that in detail in a few minutes, but they're going to use a sklearn's label encoder to give us those numbers in an ordinal number encoding to replace the number. So each category is going to get a specific number. When we do that, we get an improvement. Our MAA drops to 165,000, so quite I think about a $10,000 improvement. Approach number 3, we're going to do one hot encoding, and we'll do that using, again, a nice feature from sklearn called one hot encoder. I should have pointed out earlier that, again, we're doing the customary how you do transformations. You do the fit on the training data and the transform on the training data, and then the validation or test data, we only do transform. So here we're going to go through that. Remember, when we do one hot encoding, we create new columns or new features with the encoding. And then what to do here is we no longer want to keep the column that we use to do the encodings from, so we drop those categorical columns out. All right, when we do that, we get 166, which is not quite as good as approach number 2, I believe, which was 165 something. Yeah, so we're close, but we're not quite as good with the one hot encoding. So the label encoding worked the best in this case. Anybody have any thoughts?
I have a lot of questions, but I'll let somebody else ask their questions first.
Okay. Are there anything in the chat? I'm not monitoring the chat, so if you have anything in the chat.
That has gone viral on categorical encodings. So some quick questions at the very beginning, David. Yes. So, or maybe in the theory part. Is there any difference if you choose the default label encoding or use your own numbers, or does the scale play any role, or, just some general thoughts, basically?
Well, that's a good question. So, well, let me tell you why I have a problem with what they did. Let's talk about label encoder first. So, let's see. Can you see my screen here?
Yes.
Okay. So you'll notice here it says this transformer should be used to encode target values, the Y, not the features, the X, right?
Yep.
So first of all, they've used it in a way it's not intended to be used. Label encoding will always basically, code in terms of integers. So it's going to give you, a couple things about it. It's going to give you integers for the actual encoded results. And here they give an example of it fitting some numbers, because you may have your labels that are in your data set might be, in terms of a classification problem, might be not just 1, 2, 3, 4. They may have, strange numbers, like, there's a lot of different codings that you might be trying to predict. But it's a lot better when you're looking at probabilities and how a model does predictions for classification, to have your labels be integers that are continuous, without gaps in there. So that's one thing it does for you, is it can make those into numbers that are 0, 1, 2, right? And they do it here. They show how you can do this for categories that are object streams, right? So again, the other thing, so it puts it in a nice order like that for you. It's made to do that. And when you're doing that, you don't care about order, you just care about the value, right? The label is all that's important, because you're predicting the target, not any kind of, there's no, whether it's a 0 or a 1, there's no, 1 isn't better than 0. It's just that it is a 0 or it is a 1, right? It's a zebra or it's a horse, right? There's no, it's not making a judgment. But if you're predicting, like, numbers or something, then you might talk about that. The other thing is,
are you talking about if it's regression?
I'm sorry, what?
I mean, if it's a regression.
Well, what I mean, I guess what I'm trying to say is, your target in a classification, it's just the class, right? It's not, there's no, so the fact that it's from 0, 1, 2, 3, there's no meaning that it's 2 is bigger than 1. And the reason I'm saying that is the next encoder I'm going to show you does care about order, right? And in their example, they were using the label encoder to introduce order. And what I'm trying to say is, label encoder is not, it doesn't care about order, right? It's giving you labels. The other thing is to note that the labels it gives you are integers, and that's important too. So what I think they should have used for exactly what they were doing, and maybe someone can correct me, but I think they should have used ordinal encoder. Ordinal encoder is for encoding features as an integer array, right? So it's, the whole idea is that it's for features, and I'll show you a couple of things about it. It gives you output that is float object types, which can be important for features. It's nice to have all your features have the same type. So it can be important for some different types of models, maybe not the ones we're going to show here, but it is important for some. It makes a lot of things easier. The other thing is it is made for rank, right? So how to say it, you want to think about the fact that if you have a 2 in your feature versus a 1 in your feature for the value, the 2 is higher. And then if you have a 3, the 3 is higher than the 2, and the 1 is lower than the 2. And that has meaning in terms of order of, it's like any other value, like the number of rooms in the house has a numerical value in the actual magnitude of the value. So ordinal encoder is changing our categories, our strings or even numbers into these numbers that have order to them and have meaning in that order, right? Whereas label encoder is not intended to do any of that. So I hope that, I don't know if that's going to make sense to people, but.
Well, actually it is. Can you hear me better now?
Yes, absolutely, Chris. Yep.
Okay, yeah, I'm looking at the screen here, and it looks like it puts you completely in charge of picking which integer value goes along with which label, instead of just simply lining them up and going 1, 2, 3, 4, 5. Can you actually do them in a sort of a non-linear, almost Fibonacci increase, or some sort of other increase in the integer index that would go along with what might be the implicit distribution of the data you're trying to represent?
Yeah, so I think that let's see, fit. So here, I think when you do the transform, you can provide that target value. So what you're talking about, right? If you wanted to use, instead of just 0, 1, 2, 3, 4.
It'd be 1, 2, 5, 10, 20, 30, that kind of thing.
Yeah, so you can put that in here when you do the transform, and it'll convert them to your own targets.
Yeah, that fixes an issue that came to mind when you were talking about this. That it sort of seemed in the label encoder, it was just simply assuming that it was a straight line, which may not be the case at all.
That's right. Yep. So I would say but of course, I would only use ordinal encoder when there actually is meaning to the order to which you're, encoding these, right? So, okay.
Much nicer.
Yeah.
I agree with your points about the training, by the way.
Okay.
Speaking of ordinal encoder, David,
yes.
Is that order introduced by the ordinal encoder imputer, or is it up to our model to figure out if the order is important or not?
So it's introducing the ordering of the categories. And then the model tries to understand, like any other numerical input it gets, how to weight that. Does that kind of answer the question?
I'm saying a model that is using ordinal encoder as an input, another one that's using, let's say, a label encoder. Would the model kind of give more attention to the ordering of values, or is the ordering of values open to the model to pick it up as a feature or not?
Yes, I would say that it's not that, I wouldn't say it's the ordering, it's the kind of the magnitude, right? But what I would say is both label encoder and ordinal encoder are giving the model, replacing the categorical values with numbers that have order to them, right?
So can I answer your question directly?
Sure.
Yeah, so I don't think you're gonna have a model like learn the appropriate order, but what you could do is set up your scikit-learn model as a pipeline. So you have the data transformation step with the ordinal encoder, and then you have your model as the following step. And then as you're doing feature selection, say you're doing grid search or random search with cross-validation, you then put in different different distances for your categories as one of the features to select them up. So that's how you would, I don't know, select them. It's not really an intelligent way of doing it, unless maybe you're using hyperopt or something like that.
You're talking about selecting the actual
Order, yeah.
order, yes, right. Because, but I think yeah.
So you're
hopefully you would know for some of these categories, you might already know what order you should have, depending on your data set. But yeah, in a case where you don't have any idea and you're thinking they should have ordinal, should have order to them, yeah, you would definitely want to follow some kind of procedure like that.
I'm mostly thinking about the relative magnitude rather than the actual order.
Right.
So if I understood you correctly, Alexandra, you're saying you can actually treat this order as another hyperparameter. You can try different models with different order of your input.
Yeah. You just put it into a scikit-learn pipeline. I don't have any example ready, but that's fairly straightforward to do. If you've ever done like simple NLP, like text classification, and you use TF-IDF to pre-process your text, that's maybe an example if you're familiar with that. If you're not, leave it.
Yeah, we're going to cover pipelines after this session, so.
Oh, okay. Well, then I'm jumping ahead of the game.
No, I think it's a good point.
And last question from me. I know there's a lot of other questions. Ordinal encoder, is it used only if our input data has some kind of order in it, or can I use it for Tokyo, Paris, Amsterdam, kind of unordered list?
So I would only use it for ordered. So if your number of categories is small enough, something like Tokyo, like Paris, would probably be suitable for one hot encoding. If if it's not, so let's say you have a really large number of categories, which can happen in some fields. There are much more advanced ways to treat categorical features. There's a lot of things like you can do hash bucketing, you can do embedding of the values. So you can do much more advanced treatments that I think are suitable for a really large number of categories.
Got it. I saw a lot of questions in the chat. Robert, I think you answered some of them. Do you mind summarizing for us some of the interesting questions that were posed or some other things? I couldn't follow up on chat, to be honest. There's so many questions.
Yeah, there were a lot of questions. Is there anyone that asked a question in the chat that wants to bring it to the larger discussion? Feel free to speak up.
In my mind, I'm still not 100% clear when would you use label versus ordinal versus one hot. I understand the order is important in the ordinal part, but I don't know if it performs better or worse. So is it just a trial and error approach? Like, is there a rule?
So as a rule, I would only use label encoder for labels, for targets.
For target.
Yeah, I mean, that for me works every time. I mean, ordinal encoder gives you everything the label encoder basically gives you, except for it's made for encoding features, not labels.
And for features, you basically have either ordinal or one hot. Those are two only options.
I wouldn't say they're the only ones. They're the ones they're showing. Yeah.
Okay, got it.
I mean, the third approach was just drop them, drop the column. That was the other one. Let's see. So here's the exercise where they go through this, just to show what they did. The first approach, they dropped all the categorical columns. That gave a result of 178. Then they used the label encoding. Result there was, if I get to it, 175, so an improvement. And then they wanted to ask you to think about if you have, a really large number of categories and you do something like one hot encoding. We talked about how you're going to end up with a huge number of features because you're introducing all these new columns, these feature columns for each category possibility. And they just give an example here. I think, what do we have? 10,000 rows and a categorical column that's 100 unique category values, right? So how many, if we did one hot encoding, how many additional entries are we going to get? And hopefully people realize that you're going to, for each unique entry, you're going to get a new feature, so a new column, but you're going to also drop out the original one. So you're introducing whatever that might be. But then if you're doing that for 10,000 rows, you can figure out how many rows you're actually adding, which is a lot of new data. In some models that might be okay. It gets to be very painful though once you start getting that much data.
Question.
Yeah.
And this is probably implicit in the underlying the discussion, but if you've got categorical data like Paris, Bonn, London, that's totally, the mapping from the numbers to the categories is totally arbitrary. Does the model know that? I mean, once they're in there, that arbitrary mapping is assigned, they're given numbers instead of the labels of their city, whatever the category names are.
Mm-hmm.
Is it going to treat it as a number? And if so,
I would treat those as one hot. Right?
I would. So should you always do that? I mean, it seems like if it's going to treat it as a number, you should never use label categories with numbers.
Well,
except for the trees, right? Except for the trees, Alexander. So anytime your mapping is continuous or smooth, like in a regression or a neural network, you know, that those mappings are, you know, continuous functions. Then the order matters, and then, you know, but if it's trees, no.
But how could you have, if they're just categories like colors? I mean, and I guess colors, you could think of them on the spectrum, you know, the EM spectrum, but assuming it's just totally arbitrary categories, you wouldn't ever want to treat them as the numbers that are mapped to them that you just assign to them. You wouldn't ever want to treat those numbers as numbers.
Yeah.
Is that true?
Yeah, I agree, with the exception that if you know in advance that all you're going to use is trees, you can sort of afford the luxury of not having, you know, the wide data frame and just, you know, encode it with numbers, because the trees wouldn't care if 4 is less than 5 or.
So the trees treat everything as categories.
Yeah, pretty
basically.
much. Yes. Yeah.
Okay.
Well, they treat numbers as numbers usually, but they're able to split anywhere. So it still will make a difference in many cases on the trees. Another thing I would suggest as a consideration here is you want to think about how many possible or how many different unique values a categorical has. For instance, if it has only 2 values, then you're fine representing it as a number, right? 0, 1 allows you to distinguish between those 2 categories just as well as the names. And you know, even if there's only 3, maybe a tree-based model can do well as well. But if you have a whole lot of different categories, then trying to encode them with a integer label encoding is going to introduce some ordering that's just not that there's no meaning for it. And
I want to add something from some of my practical experience. So label encoding is useful if you are doing like a neural network. You'll probably want to encode your categories into numbers and then pass that into like an embedding layer in your neural network. And then that embedding layer will basically take your category number and create some vector that tries to like, you know, approximate this is the meaning of Japan, this is the meaning of something based on your data. So that's one use case. The other thing I wanted to point out is if you exit scikit-learn and you look at some other packages, there are tree-based models and Python packages that don't require you to actually encode your labels. So your categories could then just be used to split on your categories. So light GBM is one option. I believe Xgboost may allow you to do it. Catboost also allows you to do it. And these are all basically fancy ensembles of decision trees.
Okay.
But do they do their own encoding under the hood, Alexander, or?
Catboost has its own encoding under the hood. It's a model from Yandex that was open sourced. The other models like LightGBM will actually just split on the category natively. And if you're familiar with R, a lot of the tree-based models in R just natively split on the category itself, and you don't have to do any encoding.
Got it. Thank you.
And there's a great library in Python called Category Encoders that introduces hundreds of different ways to handle categories. You even needed, I mean, there's even like specialty considerations for, like Robert talked about, if you have like thousands of different unique values for the category, sparsity approaches and such. So it can get very advanced.
You mentioned another library with us, David, from TensorFlow feature column.
So that's a part of TensorFlow that does a lot of this automatically for you. So you don't have to call sklearn or anything like that. It does all this encoding. You choose how it handles like categorical features, but you can do all the different approaches. It handles it.
Does it have any new approaches than what we've seen so far in sklearn?
Well, embedding's built in. There's hashing. There's quite a few different ones that aren't there.
Got it. This is one of the most interesting sessions, to be honest. So much to understand and experiment with. If there are no more questions, I'll actually try a new feature on Zoom. We'll actually do a poll at this point before we move to the next session. Let me pull it up. Okay. Let's do a poll for like 5-10 seconds. Just to get some feedback from you, friends. And then later on, we can tailor them to get some more specific information. Cool. So the question is, what do you think of the Kaggle Mini Courses so far? You love them, they're okay, but you wish they went deeper. You know, I prefer other content online outside of Kaggle courses, or you don't like them. Okay, 5 more seconds. All right, and share results. Cool. So most people like it, and many of them actually wish they went deeper. Okay, good to know. Awesome.
I guess we should acknowledge sampling bias, though, right? Because we're polling the people who are actually here watching our Kaggle Learn.
Of course, bias is always included. Cool. Awesome. Thank you, David. That was awesome. That was awesome. Let me share my screen. And thank you, everyone, for pitching in with your learning experience and your coding experience. Appreciate that. Cool. I just wanted to bring in, I just wanted to share with you some of the metrics as I was training this, as I was using this competition, this Melbourne housing competition, of all the way from the very first model that we built using the random forest. What was the mean absolute error, and then adding new features to it. How does that improve our score, and how do you navigate yourself up to the leaderboard? So by the very first version, we were using the very first random forest. I think it was just 100 trees. For this data set, my MAE was about 21,000. Then I actually did another approach for missing values. I think I actually filled NAs with some values. I think I filled them with zeros. Sometimes that works, sometimes it doesn't. That gave me a good score, about 16,000 on the test set. Then I think the best of missing values was imputation. Imputation was there. I got about 16. Then categorical, about 16,000, and so forth. So it's interesting to see how the score goes as you introduce more and more features to your model. Cool. That said, we covered missing values, categorical variables. I will cover pipelines and cross-validation, and Dimitri will take us to Xgboost and data leakage next. Cool. So when I was submitting the code for the exercise that you covered, David, I was getting so lost because I had to keep track of, okay, what am I encoding for the training set? What am I encoding for the validation set? And what am I encoding for the test set? And things can get out of hand pretty quickly. And then I remember posting a question to you guys on Slack, and then I was going through the pipeline section. I was like, okay, this seems promising. So pipelines, what are they? Think of it as if you have to do all these steps that David mentioned, keeping track of missing values, keeping track of what splits you do, keeping track of what imputations you do for your numerical variables, keeping track of what encodings you do for your categorical variables. You know, depending on how many features you have, this can get out of hand. So this is where like computer science and data engineering come into place and kind of productize this whole process instead of you doing it step by step in code. So pipelines are basically a new construct in sklearn that you can package basically your step into neat, discrete steps, and then you can apply them and you can tailor them. So some benefits of pipelines, as you'll see, are much cleaner code. You can easily fine tune them. You can easily update them later. You can look at the code a week later and you can still understand what's going on under the hood. That also introduces, fewer bugs. And think about it, once the code is much cleaner, you have easier, its readability is increased, and it's easier for you to maintain. And also it's easier to productionize. So if you want to launch it as a product, you can do that easier with pipelines. And you can also introduce more options for model validation, as we'll see, which one of them is cross-validation, as we'll see next time. So again, we're looking at the Melbourne housing data set, and we split our original data set. We moved our price as our target, and then we split the rest of the features as training and validation using this 80-20% split. For this exercise, I think we kept only categorical columns where the cardinality was less than 10. So if a column had, let's say, 20 different values, we're actually going to drop that features just for this exercise. I tried with different versions of this. Sometimes it helps, sometimes it doesn't. It's interesting to see. And then for the numerical columns, we keep all of them. So that's what we do here. We keep all of them that are integers or floats. And then our final features that we're going to keep are the categorical columns. So the ones with kind of low to intermediate cardinality of less than 10 values, and the numerical columns, which are all of them. And that will be our training and validation test set. Taking a look, we see NAs, we see missing values, zip code, as you mentioned, and all that. Some categorical variables. So a lot of things to do. So first of all, we have to take care of our missing values in numerical data. We also have to take care of missing values in categorical data. So how do we do that? So from sklearn, we will import this column transformer, as well as this new library called pipeline. And we've seen already the simple imputer and the Hot Encoder for numerical variables and categorical variables before. So we will create this simple imputer transformer or object for numerical variables. The strategy will be constant. And if you look under the hood here, all of this modules, all of these constructors, if you don't specify the value, there's a built-in value that is used. I'm trying to remember what is the default value for simple imputer when you use constant. I don't remember.
It's zeros.
0? Okay.
For numerical data.
Yep. Then for categorical variables, we're actually going to define a two-step process. First of all, we will take care of the missing values. We will impute missing values with the most frequent values. So let's say we had Paris, Tokyo, Amsterdam, NA. The NA value would be Paris, simply because it's the most frequent value over the entire column. Then once we do that, we'll transform our values from a string to a number, and the number could be either a label, sorry, not a label encoder because that's for target. It could be ordinal encoder or a one-hot encoder. In this case, we're using a one-hot encoder, and sklearn also makes it easy for us when we see new values that we haven't seen before in the validation set. We're actually going to drop those values. That's this handle unknown ignore. Cool. So now we have a way how to deal with missing values for numerical features, how to deal with missing values for categorical features, and how to encode our categorical values. And then the next step would be to package all of them together. So we use this column transformer object, and we give it as inputs different transformers that we created above. We give it a name, num, for example, for the numerical transformer, and we also give it as input what features we want this pipeline or this specific transformer to take effect on. So that's for the numerical columns. And for the categorical columns, we use this categorical transformer. We package that as a one step, as a preprocessor, and you'll see how easy it is now to use this. So that's just basically on data preprocessing. We haven't even defined our model yet. Then the next step would be to define our model, and this is a simple model. We'll look at some more complicated models soon. Then our metric, how we're going to validate how we're doing compared to our actual values. Then the same, so this is the preprocess that we saw above, which contains both the steps for the numerical and the categorical variables. We can also pack in there the model itself. So now basically we're packing the pre-processing and also the data processing or the modeling part into one pipeline. Once we have that pipeline, we call it a fit method on the training and on the training features and the training target. Then if we want to take predictions out of it, we use the predict method on the validation set and we get our predictions. We have our model predictions. We have our true predictions. We use the MAE, the mean absolute error function from sklearn, and we get a specific value, in this case, 160K. So basically you saw how easy or how concise, clear the code looks at this point compared to what we had before, where we had to take different steps for different features for the training set, maybe the validation set, and maybe even the test set. Is there anything else I missed here, David or Robert or Dimitri, or any questions? Let me know. Otherwise, I'll jump to the exercise. Cool. I'm not monitoring chat, so let me know if there's any questions. Awesome. So the exercise, I think the training set is slightly different here. That's why the numbers you'll see are slightly different. So again, let's look at. So we import our train test split, pandas. We read the training set x full data frame and our test set as x test full. We drop the target value, or the target feature we're trying to predict, the sales price. Then that will be our x full. Then our y will be our target. And we also, in the x full, drop any record where we don't have the sales price for. So if there's no sales price for in the data set, we can't really predict much of it. There's not much we can do about it. So we drop those rows that are missing sales price here. Sorry, this drop NA, it's actually different. It's not dropping just the sales price, actually dropping any row where there's at least a missing value in any feature. So this is usually not a good idea, but I think for this exercise, I'm not sure why this would be useful.
I think that's actually your target class.
Oh, I see. Yeah. So yeah, this is what I was saying before. So you're dropping any row where the target, where the sales price is missing. Then you set the target as the sales price, and then you drop it from your features so that you can do your modeling. Cool. Then we use this 80-20% split, as we saw before in training and validation. Again, we're going to keep for categorical features only cardinality less than 10, and object type is object. And for numerical columns, we're going to keep all of them. Nothing, no filtering done here. We're going to combine both lists into one major list, my columns. We're going to create copies of our data frames so we don't impact the original data frames, train, validation, test. And I wanted to see how many did we drop, if we dropped any with this cardinality less than 10. So the shape before and after looks pretty much the same, except for the one feature that is missing, which is the sales price. So I wanted to see with this cardinality less than 10, did we omit any feature? And it looks like it didn't, because we just went from 80 to 79. In other data sets, this would have made a bigger difference. We would have gone probably from 80 features to like 75 features. Cool. So then this is me looking around some of the issues that you mentioned, David. For example, for label encoder, they can only use it for target, not for features. That's one. The other one is if you try to do ordinal encoder, which is an option. When you're trying to do validation, you might come up to new values that you hadn't seen in your training set before. So when you fit, so basically when you're creating this ordinal encoding, you are seeing all the values in the training set. But then when you do your validation, you might see some values that were not there before and you haven't assigned them any value. So you're going to get an error there too. So that's why I ended up, I think, going with one hot encoding because it takes care of both issues. Again, the column transformer is what is going to combine all these steps for us, and the pipeline is the model, that the object that will combine the column transformer as well as our model into one object. Label encoder, ordinal encoder, this is me experimenting. One hot encoder, I think I ended up using that. We'll use a simple random forest here and an MA. And for numerical features, the constant value for simple imputer for missing values will be zeros. And for categorical variables, the most frequent, we'll be using that to fill NAs, missing values, and we'll be using one hot for to encode them. Yep, if you try to use anything else, you're going to get those errors that I mentioned above. Then we bundle this column transformers into one column transformer object. We have a pre-processing step, we have a model, we combine them both using a pipeline, and we have our model and our pre-processing step into one object. We feed it using the training and the X-train and Y-train. We predict using the predict method. We get an MA of about 17,000. Cool. So this is our baseline basically for this data set. Using this specific options for numerical and categorical transformations, this is what we got. Now the exercise goes into a little bit more detail of, okay, can you try different values? Can you try different imputations for numerical transformer or different imputations for categorical transformer, maybe a different model. So these are basically a hyperparameter search space. This is just some information from the simple imputer. Yep. So you can do for numerical variables. You can do mean, median, most frequent, constant. Most frequent can also be used for strings. Constant can also be used for strings. Mean and median can only be used for numerical data. Cool. Then I think I tried different ones, and I think median for numerical for imputation and constant for categorical instead of most frequent, I think gave me the best results. I think so, yep. Let's see, did I try anything else? And then the, yeah. So the goal was basically to try different values for imputation, different values for missing numerical, for missing values in numerical features, for missing values in categorical features, as well as this encoder. So for me, using the sklearn pipeline, this was the only option for me. Just glad to hear that there's other options as well. Cool. I continued with this notebook. I added more and more features, but those are, I need to explain them first before I take a deeper dive. I haven't monitored the chat, so let me know if there's any questions or feedback or comments.
I mean, I will comment that I found it hilarious that when they teach you label encoder and then when they actually put it in a pipeline, they realize, oh, you should be using ordinal encoder.
Yes.
I have a question about the simple imputer.
Mm-hmm.
And this is just something I noted in my notes from when I did this course like a year and a half ago. I don't know if it's still there, but I was looking at the variables, and one of them is verbose, which they note is an integer. And then the definition, and when I say they, could have just been from the documentation on it, controls the verbosity of the imputer. Well, that wasn't very clear to me. So I was wondering if you could explain better what that means, what the verbose means.
I didn't try it. I assume you'd get some more information on maybe how many missing values are there and what was the value imputed. I don't know. Has anybody else tried it? We can try it next time, I guess.
I mean, I can't speak to it this function specifically, but in general, verbose just means it prints out, additional information. If it's 0, of course, it prints nothing. If it's 1 or some other numeric value, it'll print out some information related to what it did.
Mm-hmm.
I don't think I've ever encountered a variable named verbose that changed the functionality of the actual function other than just what it prints.
Mm-hmm.
Got it. Thank you.
I saw this other feature or option, add indicator. I haven't played around with it, but it allows you basically to look at other columns. I'm not sure.
It looks to me like what that's doing is doing your third strategy for missing values, where you're not only imputing it, but also adding another feature that indicates whether it was missing to begin with.
Oh, I see. Okay, that's not what I mind then.
This makes sense. In a lot of the data that I look at, the fact that a data point might be missing is actually very informative. So like if it's missing, then that might mean that a particular thing doesn't have some attribute at all.
Mm-hmm.
Right. It can be very important to distinguish between the data points that are the mean just because that's what they were in the data set versus the ones that were just assigned to the mean because they're being imputed. I mean, I guess it's another bias variance trade-off in the sense that it gives your model the flexibility to be able to treat those cases differently in case it needs it, at the potential cost of introducing noise if that's not a useful thing to do.
Got it.
I would argue some of it's data dependent.
So there was an earlier question about how to handle those missing when it's categorical. And so this is one way is, you can do your encoding and, then make this, when you're missing, do those, right? Ignore. Or you can put an actual value in place of missing values, like something like NA or missing. So a unique value that indicates missing,
mm-hmm.
and then do your encoding, your one hot encoding or no encoding or whatever.
Isn't that the same as doing simple imputer by you giving the field values? I don't know if you can do that. In the simple imputer, can you specify this field value?
Yes, sure. Can be used with strings or numeric data.
Yep.
Yep, that's how you would do it.
Okay, I like that. Cool. In the interest of time, I'll jump to the next session because I want to give as much time as possible to Dimitri as well. So the next session covers cross-validation. And just to give you an idea of the intuition is, let's say you have your entire training set, and then we did the 80-20% split. But let's say for some reason that 80% didn't really cover a good representation of your entire data set, especially if your data set is imbalanced. Let's say you're doing some kind of fraudulent transaction, modeling or classification, or I don't know, medical data set where you have such rare instances of diseases. If you do that 80-20, you might have a data set that you might not even find a good or positive outcome. So in that case, your model might do really well in training tests because you'll pick up the features in the training set. But then when you roll in production or when you expose it to the test data set, you might do really poorly because you don't really see a lot of variety in the data. So the whole point of cross-validation is saying, okay, let's make sure that we really cover, really learn different features from the training set. And to do that, we can do what is called a k-fold cross-validation. So in this case, let's do a 5-fold cross-validation. What that means is that we have our total data set, and we break it apart into 5 if we're doing a 5-fold cross-validation. And we do different experiments. Okay, in the first experiments, we're going to keep the first 1/5, let's say 20% of the data as validation, and the rest of them will be our training set. So we'll do our our modeling, we'll do our prediction, we'll keep that model, we'll keep that output first. Then the second one, we'll use the second 20% batch as our validation, and the rest as training. Then the third one, the third, the fourth, the fifth, and so forth. So basically we have 5 different models that each of them are exposed to different subset of our data. And really the goal to do this is to make sure that our at least one model is exposed to, or collectively all the models are exposed to all the different training data set. So when would you use it? Curious to hear your thoughts as well, but if you have smaller data sets, using this is pretty straightforward, and you've seen Scalar and how it's done. It's highly recommended that you do this. When you have larger data set, given that this will take basically 5 times longer because you're training 5 different models, maybe this is not the best approach, or maybe you can try a smaller fold, and instead of 5-fold, and you can do a 3-fold. I'm curious to see if training size is the only parameter that you use when you do this. I'm curious. Let me know.
So I have a task that I'm working on where the data is so big it won't even fit into memory. So I am not using cross-validation for this data set.
Okay.
Yeah, I mean, I just slice off like however much I want for test data, and generally it's representative.
But let's say, I mean, I can see this being useful when you're doing some kind of overfitting scenario. Would it be useful to just maybe drop some percentage of your training set and just do 3-fold? Would that be more useful to avoid overfitting, or you just don't do cross validation at all and you just deal with overfitting with other methodologies?
For my use case, I'm just having trouble finding a model that works for what I'm trying to do with the data that I have. So I'm not even at the point of like model selection.
Yeah.
So I don't know if this is helpful to other people, but I mean, these sorts of things do happen. For smaller data sets, I mean, certainly we'll use cross-validation to help select a model and verify that, yes, this model works well, especially when the data is too small to really have a good train and test set split.
Awesome. Cool. So let's see how we go ahead.
I'll just throw some perspective out there. I personally, it's only for small data sets that I use it, but I know, since we're talking about Kaggle, for many of the leaderboard, winners of competitions, even with really large data sets, they religiously apply cross-validation.
Okay.
I don't, maybe when it's important to get like 0.1% better, accuracy or something, maybe it is crucial even for larger data sets. I'm not 100% sure of the reasoning, but. Okay.
So it depends if you have time and resources and how important it is to you.
They do have, yeah, often they have a lot of resources. So that's a big deal.
Yeah, I think so far we've had compute constraints. And so with larger data, we just don't have the compute and the time, when oftentimes a model that's good enough will get us like most of the way there. And it's not really worth the effort to get that last little bit of accuracy. But this is more of like a in practice answer than a academic answer.
Mm-hmm. Got it. Thank you.
But even academically, there's also diminishing returns.
Yeah. And also, you wouldn't see much of a cross-validation in deep learning, right? In TensorFlow, I don't think they have a separate
oh, really?
An API for that. Do they have that?
I haven't come across it. No.
Yeah.
It's interesting.
Yeah, it's usually done by hand.
Yeah.
Yep.
It's just too costly, it trains for hours.
Cool. All right, so let's see how we use it in practice. Again, similar data set, just consider a subset of the features. Select our target, which is the price. We'll use a random forest, a pipeline, a simple imputer. The default features, whatever those features or settings are. just 50 trees for this random forest and a random state for reproducibility. Then from model selection, we will import this cross-val score, which is basically how we do cross-validation in sklearn. And looking at their documentation, I think they have this convention that the higher value, the better for score. So we have to introduce a -1 when we do this scoring for mean absolute error. And the way we use it is we give it our pipeline as input that takes care of pre-processing as well as our model, our features X, our target Y, and then just one simple variable, CV, how many crossfolds you want to do for X, 5. That means that it will do 1/5 as validation, the rest is training each time it runs this model. And for scoring, we'll use this negative mean absolute error. Cool. So running this 5 times, you'll get 5 different scores, 301, 303, 287, 236, 260. So it looks like this is the best one, giving us the lowest MA. Then get the average across all of them. It's the average of the list. And then, sorry, I forgot to mention that the model that is that is trained under the hood, right? So that model is exposed to different data. So the model isn't really changing, right? The model is not really changing. All you're changing is the data you're exposing to the model. Just to clarify my own understanding.
So the model architecture is not changing, but are you, the question, I think there's a question in the chat that has to do with, are you reinstantiating the starting weights of the model and all that and training it from scratch each time?
That's a good question. I don't know.
Yeah, I'm pretty sure it's being trained from scratch on each fold.
Yes. The reason the question was asked is the thought was that say you start the next fold, you know, if you use the weights from the prior training, the training would be a lot faster, right?
Each model is completely separate and independent when you do cross-validation.
Yeah, my thought was if you use the weights from the prior one, you're introducing data leakage, right? I mean,
yeah, plus I think a lot of the classical models that you see in scikit-learn, you can't really update weights.
Right.
Really. So.
Right. My question, I posed the question, but to me that almost seemed like a transfer learning type thing.
That's what I was about to say.
Kind of very similar in some way.
Yeah. So that's not supported, I guess, in sklearn, or that's not a good idea. I'm not.
It's not supported. Yeah, I think there's some newer Python libraries that allow you to update models, so like online learning. So you get a couple observations at a time, and then you update your weights. Mm-hmm. And you can do that with linear regression, but scikit-learn doesn't support that. You'd have to look at another library.
Keep that thought too, because the next section that Dimitri is going to cover, I think we're going to get there, where you try to take the best out of what you have and improve it and improve it and improve it.
Okay.
Cool. Let me very quickly go over the exercise. I don't know if there's anything different than what we saw. I think just the data set is different. Yep, so drop the sales price and drop any values, any rows that their sales price is missing. Nothing specifically for categorical variables. We're keeping all the numerical ones. Oh, for this exercise, I think we only kept numerical columns. I'm not sure why. And the pipeline is very simple. You just need a simple imputer and your random forest. Your 5 cross-validation gives you a benchmark. And then I think we're going to try different models. So let's see. So we write a function that basically defines the pre-processing step, our random forest. And the only argument is how many trees you want to try in your random forest. The CV could also be another argument. You can experiment with different ones. And then what we did is we tried different number of trees for our forest, and we looked at so we tried different number of forests, and we looked at the one that had the lowest one, and it looks like around 200 trees we have the lowest MA. So then we take that, and I think we can use some more hyperparameter tuning, or we can explore more other options, but keeping this parameter now fixed at 200. Cool. If there are any questions, let me know. Otherwise, I'll hand it over to Dimitri of how do we do kind transfer learning in sklearn, if you want to say that. Let me stop sharing.
Okay, can you see my screen?
Yes, call out.
Yeah, so I'll try to be very quick in the interest of time. So Xgboost is a particular implementation of the gradient boosting algorithm. It was suggested 4 years ago, and since then became, the #1 tool on Kaggle and more generally in the industry. So my original plan was to talk about the reasons why would you use Xgboost and use cases, and then go into some theory, and then go through a notebook when we apply Xgboost to Melbourne housing data. But I think, in the interest of time, I will probably skip the theory. I have links in the notebook, and I'll post it on Slack. So first, I was going to talk about the use cases for Xgboost, and especially, comparing and contrasting with other models, like, for example, simple linear models on one side and neural networks on the other. So just very quickly, Xgboost is today probably the default model for all kinds of tabular structured data, right? Where when you have basically think about the database, relation database, basically records of objects. Each object comes with a set of features. Features can be heterogeneous, some numerical, some categorical. And then you have to do some prediction on some attribute of those objects. So that's exactly the use case when you would use Xgboost, as opposed to, for example, neural networks. So it works well on non-perception data. Like, perception is the neural networks domain, right? The vision and audio and text, etc. Because the features are not immediately obvious and intuitive, and there is some complex hierarchy among the features. So that's where Xgboost is worse than neural networks. Xgboost, together with neural networks, basically are very powerful nonlinear approximators. So Xgboost can approximate any function because basically it's a very large ensemble of trees, and trees are piecewise constant functions, so can basically approximate anything. As opposed to, for example, a very, you may have a complex linear model or a polynomial, but it's still, the capacity is still limited, and it will, overfit quicker than Xgboost. So Xgboost is robust. It's robust to outliers also, like in the Melbourne, in the housing data set, we may add, maybe an erroneous data point with, I don't know, 1 million square feet. Xgboost wouldn't care because for Xgboost, basically, whatever the actual value of the variable is, that doesn't actually affect the tree that is building. Also, in contrast with neural networks, Xgboost is explainable. So it gives you a nice picture of which features are important, which are not, but it doesn't give you a direction. So it will tell you, I use, for example, the square footage or the number of rooms maybe 80% of the time, but it doesn't tell you, whether it's a good thing or a bad thing. How exactly does that affect your target? Again, most of the linear models are telling not only the magnitude of the influence, but also the direction. In Xgboost, you don't have that. And one final point I was going to make is, the first thing you would read about Xgboost that it's a Kaggle winner. All winning teams are using Kaggle Xgboost, but it's actually widely used in the industry. So it's the preferred tool of choice. So very briefly about what Xgboost is, compared to the trees generally. So this is a nice evolutionary path. It starts with decision trees, like simple decision trees, when you split your variable space into disjoint areas, and then assign some value for those subspaces, and basically that's how you describe your X and Y mapping. Then a slightly more involved version is bagging, when you basically combine, you ensemble many trees, and your actual prediction, your final prediction is basically an average of many trees of a similar structure. Now, random forest is a modification of bagging that adds random sampling of features. So for each tree in the ensemble, you don't use identical trees, but you use some modified trees. Maybe some tree uses only some portion of the features, and the other tree uses the other portion of the features. And when you have many such random trees, they tend to perform really well, which was discovered, I think, in the 80s or in the 90s. So those things are pretty old already. And the basic idea behind random forest is that it helps reduce the variance, basically fights the overfitting in the model. Now, boosting and gradient boosting. Let's talk about gradient boosting straight away. And so boosting is an idea of building an ensemble, but sequentially. So at each iteration, you basically fit some residual or something that is left from the previous stages. And so iteratively, by building new stages, new models, you fit the data better and better at each point. And gradient boosting is a specific realization of that, which uses actually the loss function that you define, which propagates the gradients back through the trees, much like neural networks, but it fits. The gradient is defined in the functional space, so it finds the function at each iteration that fits the residual, optimally. And Xgboost is a specific implementation of gradient boosting. I'm not exactly sure, which optimizations they did. I think, some of the steps are parallelized. I think, it's used for classification and regression equally well. And, I think it's just a very effective and efficient algorithm computationally. So I'll skip the math part, but it's a very good description of how the whole algorithm works, just on the Xgboost help page. And then we'll go directly into the Melbourne dataset. So I just visualized the price. This is Australian dollars, so don't be confused with 8 million. and building area is in square meters. Yeah, there are about 20 predictors, but they only select 5 of them. Then I split the training and validation into 2020, 2080. I'm sorry. So Xgboost has a sklearn wrapper around the algorithm. So it's called XGBoost register, and then you call the same methods as you would do with any other sklearn model. So fit, predict, and all of the others. So first we just fit the basic XGBoost regressor. The only thing that I specify here is just I use square there, which probably I couldn't even maybe that's actually I think a default. I'm not sure. So we use it out of the box as it is, and we get the mean absolute error of 225 on the train set and mean absolute error of 241 on the test set. So I have this line here just to give you an idea of how many parameters it has. So from the depth to learning rate to number of estimators to all kinds of regularization parameters. There are about maybe 40 or so parameters in the algorithm, and we're not going to go through all of them, but I have like the most important ones here, at least for this problem. So the most important ones, the key ones, are the number of estimators, so the number of steps you take basically in your gradient boosting algorithm. And then the maximum depth is the size of the trees at each step. So for example, this configuration is, use 100 steps, and at each gradient boosting step, use a random forest of depth 3. Learning rate is describing, how aggressively you go into the direction that the gradient boosting is telling you to go. These are the regularization parameters, gamma, alpha, and lambda, and we will not be playing with them here. But basically, what they regulate is, how responsive the algorithm is to the training data it sees. Like for example, this gamma is basically the gamma 0 is letting us split the new node anytime. If I have gamma equals, like for example, some numbers, say 1,000, then the tree will split only if the the additional basically gain in or the reduction in the loss must be bigger than this gamma for the tree to split. So alpha and lambda are the L1, L2, and also an important family of parameters is how much of the features are we taking at each step. So basically, the column subsample column, this parameter, the 1 or some other number, is basically regulating the capacity of the random forest. So if this is 1, as we have here, so at each step it will take 100% of the features. But we may have like 0.5, for example, and it will randomly take 50% of the feature, at each step, or at each node, or at each tree. So this is a pretty flexible set of hyperparameters, and going through all of them, through grid search or some other method, actually is computationally pretty expensive. So I tried to go through some of them using the 5-fold cross-validation. So first, we try to locate the optimal learning rate in the number of estimators. And so, in the sklearn, there is a grid search cross-validation that was described earlier. And so you feed this grid search cross-validation with the parameters you want to test, basically. And you identify the criterion to find, to optimize, and then the grid search basically does its job. In this particular case, it found that the learning rate should be default 0.1, but the number of estimators should be 1,000 as opposed to 100, which was default. And so, by using this, by finding these optimal parameters, our test error went from 241 for the default configuration to 219. So this is much better. Now then, we fix the learning rate. We don't play with the learning rate anymore. We just quickly try to find whether the depth 3 is the good one, and try a few values here and to the left and to the right. And so it tells us that basically we should leave it at 3 and number of estimators 1,000. And then yeah, the last thing I tried is the column sum sample. So for each tree, let's see which portion of the features I should try. And there are only 4 features, so in this particular case it doesn't make much sense. But for example, in the Iowa data set, there are like 70 features, and then it could save you a lot of computational power, and also it acts as a regularizer. So this thing is used a lot, and it selected 60% of the features each time, turns to be optimal, and the test error again went down, although insignificantly, but still it does perform better than the full model. So one thing, as I said, Xgboost has, for example, in contrast with neural networks, is the feature importance, and it's just called like that, model.feature importance, and you select the best estimator from the previous step, and basically these numbers are the percentage of times the algorithm used that dimension, that variable, as the splitting point, so as the splitting variable. And so the more it uses this variable, the more influential, the more important this variable is for reduction of the error. And so this is how it looks. I think this is an example of rooms and building area probably be correlated. This is a separate thing, separate question to be answered, but that's what we get, and it does make sense, right? So the number of rooms and building area are more important than the land size, and probably more important than the year built. But I just thought it's important to show some of the other functionalities that Xgboost has, in addition to what they have in the Kaggle page. Yeah, and this is just to visualize the residuals. Like for example, there are some points that Xgboost didn't pick up, like $3 million of the true price, and it just tells us that the variables that we have are not far from being enough to describe the price of the house. So I think that's it for the Xgboost, and please let me know if there are any questions before I move to data leakage.
Thank you, Dmitry. This was awesome, and thank you for sharing your notebook with us. I had a question. I loved your approach where you did a different grid parameter search for for different parameters. You started with learning rate and number of estimators, then you found the best ones, you plug them into your next step, and you played with other features. Question for you is the order important in which you do this, or it depends on your scenario?
No, I think it depends, George. This is poor man's optimization, right? So don't have much compute, much time, etc. So it's like the greediest way you can go from the most influential features down to less influential, and try to sort of optimize that way. But of course, if I had more time, or if this would be a real life problem, you would do a real maybe random grid search through the parameter space. There are not that many parameters, like 4 or 5 key parameters, and it's quite possible that the best configuration is not along this line, along this greedy line that we selected. So
got it. Another question I had for you is, in the very last model, you were looking at different subsets of features to consider.
Yeah.
Is that used only during training, or is that actually used during validation as well? So for example, let's say the best model kept only 60% of the features. Does that mean that your model now expects only a specific 60% of the inputs, or you give it everything you have as input, and then the
that's
model...
a good question. I don't remember. I would suspect it's used only during training. Because the sampling is done randomly. This is the random sampling of the available features at each step during training, and so I suspect it plugs back all the features during inference. But that's a good question.
Got it. Cool. Thank you, Dimitri. Any other questions for Dimitri? So there was a chat online about, on the chat, about other models like GBM or Xgboost. I haven't used either of them. Have you used them, Dimitri, and how do they compare with Xgboost? Do you know?
I tried to compare LightGBM to Xgboost. Didn't see much difference in one of the previous exercises. So, Xgboost seems to have the reputation of being faster, but in terms of performance, I haven't had much sort of comparison done between the two.
Got it. Thank you for sharing the theory as well. I'll go over it. I'm curious how that gradient descent works in terms of training. Cool. Can you go to data leakage? Yeah.
So data leakage, I'll be really quick here. So they have this page on Kaggle, right, on the tutorials, and we can go through that, but let me very quickly go through the basic idea of what they're trying to say. So there are 2 types of data leakage that they describe. So the first is your training, your test data leaking into the training data, and that applies to I would say to any machine learning setting, right? Supervised, unsupervised, whatever you're doing, this is the #1 rule that you should follow, not to allow your test set to leak into the training set, because your objective is to build a model that generalizes to unseen data, and test set is as best as you can get to unseen data, and so you should separate that and don't touch it at all. So the good sort of the hygiene requires that you just separate it even before you do any pre-processing, any scaling, imputation, etc. Just put it completely separately. Just before that, of course, you make sure that that your test data is sort of representative of your true population, and is actually valid. So that's #1, and they stress it, and rightfully so. #2, a little more subtle point with the validation set, And validation set is, of course, something we use for hyperparameter tuning and choosing the right hyperparameters. As opposed to the test set, you see it most of the time. You would impute, scale, etc. With the entire training set. So with this entire training data, it's not that you don't touch it, but again, they make the point again very very rightfully so that the hyperparameter optimization should not be done on the training set itself. It should be done using a validation set. And if you have enough data and if you have enough compute power to do cross-validation, that's even better, as you described, George. So that's basically the point they make, and that's the first type of leakage. So when something leaks from the test set, it's basically bad and makes your test predictions almost useless. That's one. And then if the validation set also leaks into the hyperparameter choices you make, it's also bad, although not as catastrophic as the test set. So that's the first point that they make. Now the second point they make is let me go into their the second point they make is more subtle. And if this first type of leakage is universal, as I said, it doesn't depend on your particular algorithm, etc. So it's like a general rule. Now this the second type of leakage happens even if you separate your data points very carefully from each other. Then even within a data point, there might be a leakage between the variables, right? So basically between the columns. Now you're done with the rows and you're good, but some of the columns may be leaking, and so that happens when especially in the time series prediction context, when basically your predictors contain some information about the targets. Like, for example, if you're trying to predict the S&P and your predictors contain the value of the NASDAQ of the same day, that's of course very correlated. So the covariate is there, and so whatever prediction you would get on your target would be pretty much useless. Sometimes it's more subtle, like they describe a good example here, like some of the it may not be immediately obvious because many variables don't have a timestamp, and so sometimes it takes you to go into the data dictionary and detailed description of what this variable means to really understand whether at inference time in real production setting you would have actually that variable. Like, for example, coming back to the housing prediction, if, for example, we would have a variable named like broker's commission, right? It's of course it's telling us a lot about the price, but at inference time you don't have that data, and so you need to really understand where each feature comes from and eliminate those that may have some influence, basically some leakage into the target. They focus here on the sort of on the time aspect, but again, generally it takes you to go to really understand your features and make sure that basically if you imagine yourself at inference time, that you only rely on those that would be actually available at inference time, and not anything, not use anything else. So that's another type of leakage, more subtle, more difficult to catch. And this type, the first type is actually like if you're careful enough, it's easy to control. This thing happens all the time, like for example, in financial applications, this is a real problem, and so we need to be real careful. Any questions on this?
I like both your analogies of S&P and NASDAQ as well, the commission fee for the brokerage. Very good to remember. I had a question that kind of ties back data leakage with the pipeline and the imputation that we did.
Mhm.
I haven't digged into the documentation, but when you set up a pipeline and you have your training set, your validation set, and you say you do, let's say, an average, like a simple imputation on average, does that only take the average for the training set, or does it consider training and validation? So they have some kind of leakage there.
In their notebook, you mean, or?
To fill in missing values. So let's say you have missing values in your training set, you have missing values in your validation set for one feature. When you do
Yeah.
the imputation, does it only consider each set separately, or does it mix them?
It depends on how you set your pipeline. So I'm not sure, how exactly the implementation goes. But as I said, I think it's not that important with respect to the validation. So, for example, as I said, the scaling. If you want to be sort of scientifically clean, you would probably do it separately. But things like scaling, imputation, with respect to the validation set, is not like super important to keep it separately. In contrast with the test set. So test set you don't even touch. You don't know where it is. And the validation is basically, you could be a lot more sort of flexible with that. Yeah, as a practical point, and I would love to hear if people have the same experience.
David, were you about to say something?
It wasn't me.
So let's say when you do test, right? When you do prediction in the test set and you get a record with missing values, are you able to perform prediction there? Do you use some kind of imputation just on the test set, or how do you deal with that?
Well, you imagine, what would you do in real life, like at real-time inference? What would you do? You do exactly that. So if you use nearest neighbor imputation, and a data point comes in with missing values, you use your algorithm to impute. If you dropped this data point, you would drop the data point. So you imagine yourself at production time, and then you answer those questions.
Okay, another approach would be to keep track of what values you've seen for that feature on the test set only, and then maybe use their average to impute.
That's, yeah.
Like moving average imputation. Okay. I don't see any other questions online on the chat. Cool. Thank you, Dimitri. This was awesome. And thank you for introducing us to grid search. We haven't seen it yet, so that was cool. Cool. I'll just want to say a few words if you stop sharing, and then we'll wrap up. Awesome. Thank you, friends. This was awesome. If you enjoyed this session, next we have actually a collection of them coming up. So we have a month full of adventures. Next Wednesday, we're going to cover pandas. And next Friday, we're going to cover feature engineering. Then after that, we have some more interesting sessions covering introduction to deep learning. So for us, we've taken the TensorFlow in practice specialization. I think this is a relatively easy module. Then we'll take a deeper dive into SQL from a data science perspective, an introduction to SQL and advanced SQL, some data cleaning furthermore, some geospatial analysis, and some other features. And David just noticed that Kaggle actually introduced a brand new module today on computer vision. So it looks like it's covering convolutional classifier, ReLU, max pooling, sliding window, custom data augmentation. So looks to me like all of this concept we've seen them before. So it should be a nice nice session for us. I'm trying to find where to fit this in our packed schedule here. So if you have any ideas, let me know. Cool. With that said, this recording will be uploaded tomorrow, available on our YouTube playlist. And I want to thank everyone for sticking with us. This was a long session, but I really appreciate your patience and feedback, and really the high volume traffic of chat. I will save the chat. I'll probably share it on Slack. So if you want to join us on Slack, you can do that. Cool. With that said, friends, thank you everyone, and have a great night.
Good night, everyone. Thanks.
Okay,
Thanks,
good
Dimitri.
night.
Thanks, Robert. Thanks, David.
Thanks, guys.
Thank you, everyone.
Thank you, guys.
Thank you.